When we put, right, this is a plane strain 2D problem. So when we put the strut in here, and I told you that the model for the strut was properties, define liners. We put in this 8-inch standard pipe. Well, in the model, what's actually in the model? I'm putting in a pipe and I'm putting it at some spacing, right? So that particular property, this is an 8-inch standard pipe at 5 feet on center. Well, how do I do that in a plane strain problem where everything's per foot into the board? How do I put how do I model something that actually changes in the y direction? Because what I'm really putting in there is a continuous beam that goes all the way across the whole length of the excavation, right? Just like I am with my sheet pile. Sheet pile is easy because it really is that way, but how do we model struts or discontinuous? So I gave you, I loaded a paper to read. It's a really, really simple, really, really easy paper to read. So what we're really doing is we're going to take, this is the model they use in rock science, because they do a lot of modeling where you've got a liner for a tunnel where you're going to have sets, which are really basically beams, and in between you're going to shotcrete. Well, both of those have different flexibility. So this is the model here is where you have two different materials in your support system. One is would normally be shotcrete, and the second one is going to be some kind of a structural element. But the bottom line is you've got a material, you've got one material with one moment of inertia, one modulus, and one area, and a second material with a moment of inertia, modulus, and area. And what you're going to do is you're going to convert that into an equivalent material, an equivalent rectangular continuous beam, if you want to think of that, of the composite material. And it's not going to be either one. And so what you have to do is go compute, and this paper tells you how to do it. It's actually pretty simple. You got to compute an equivalent height of the continuous beam, and you got to compute an equivalent modulus for it. And that, when you do this, it allows you to calculate both the axial and the moment stresses correctly. So it tells you how to do that. In rock science, you can do in the phase 2. I'm sorry, you can do that by if you go to properties and define a liner. Let's just add a new one. When you go to define a liner, there's standard beam, which is basically a continuous rectangular element. So, and then there's a bunch of other things you can do here. What you want to do, this makes no sense whatsoever, is you pick reinforced concrete. They picked reinforced, again, a lot of the nomenclature of this has to do with tunneling and rock mechanics. So when you pick concrete, what it really allows you to do is to build a composite liner that's made of two materials. It really has nothing to do with concrete. It just allows you to put in two different materials. Well, in our case, we really only have, well, we have two materials, but one of them is air, and the other one is a structural element every so often, right? So all we have to do is not use the second material, and for the first material, you go in and put your spacing. You put in your section depth, you put in the area of your section, and its moment of inertia, and its Young modulus. And what it's going to do is back calculate the equivalent beam for you. So if you're putting in a H section or a pipe section or something for a strut, or if you're doing H piles and you're putting one in, you can't just go in there and stick an H pile in, the properties for an H pile, because what you're then doing is saying basically I have this continuous H pile that runs the whole length of the thing. Now what I did for these pipes, I did this by hand because I wanted to make sure I wanted to see what I knew what I was doing. So what I did is I put in a standard beam, but I calculated the thickness of the equivalent area, the equivalent beam, using these equations, because I wanted to understand what the hell I was doing. So I calculated this equivalent thickness, and the equivalent modulus. And then I just put those into here. So this is, if I did this correctly, this is an 8-inch standard pipe. I looked up the properties of that, and I calculated the equivalent rectangular section, continuous rectangular section, and put that in there. So when you're doing these finite size elements, you've got to do that conversion to model you're basically taking your pipe that are 5 feet on center, and you're smearing them along as a continuous beam through the thing, and you got to do that correctly. Is that clear? Okay. So, what I would, what I'd like you to do, the first thing. So, what I'm going to have you guys do is take this problem with and use the strain hardening Karlsruhe model, the strain hardening. Actually, let me stop the